Hello everyone, and welcome to our second lecture in abstract algebra. In our first lecture we talked about binary operations. In our second lecture, and perhaps our third lecture also, we're going to be talking about groups. And first thing we do is define the concept of a group. The non-empty set G, together with the binary operation star, form a group denoted open parentheses G comma star, close parentheses, exactly when the following four group axioms hold. So note first of all, in order to have a group, the first thing we need is a non-empty set G. G has to be non-empty. And we also have to have a binary operation, star, on G. Now we have to have the following four axioms hold, the group axioms. And the first axiom is that G is closed under star. And you know what? I put this in even though it's not necessary because some texts don't define or don't require star to be closed on a set G in order to be a binary operation. But according to our definition of binary operation, this thing has to be closed on G. In other words, for every pair of elements in G, this binary operation assigns that ordered pair a third element that's also in G. And that means that the binary operation is closed. If every ordered pair of elements in G is assigned another element from G by this binary operation. So this is somewhat redundant because our definition of binary operation requires that it's closed on the set B, on the set G rather. Anyway, first condition, our binary operation has to be closed on the set G. Every ordered pair of elements in G is assigned another element in G by this binary operation. The second thing that we require of our binary operation and of our set G is that the binary operation is associative on the set G. If the binary operation is not associative on the set G, then we don't have a group. The third axiom, in every group there exists an element, and we'll call it little e, such that E star x equals x and x star e equals x for all elements x in G. So in other words, E star anything is that anything, and anything star E is that anything for all elements in G. And the fourth group axiom that has to hold is that for each element in G, there's a corresponding element in G such that y star x is the identity, and x star, that same element y, is the identity. And we call y the inverse of x. So every element x in G has an inverse that we call y. And the property of the inverse is that when we multiply x by the inverse, we get e, the identity. And notice something. If y star x equals e and x star y equals e, then according to this definition, y is the inverse of x. But according to this same definition, if y star x is e and x star y is e, the identity, then x is also the inverse of y. So the elements of a group come in inverse pairs. If y is the inverse of x, then x is also going to be the inverse of y. Now, as we did in the first lecture, let's look at a lot of examples. You know, I just said that we were going to do a lot of examples, and I don't want you to think I lied to you. I was telling the truth. It's just that I need to insert a couple of remarks before we start doing examples. This seems to be the best place to mention the points that I'm mentioning here. And the first point is that we make an observation. Note that while the definition of group stipulates that star is associative, the definition of group does not require the binary operation to be commutative. The definition of group doesn't require that the binary operation be commutative. Consequently, in some groups, star will not be commutative. So we have some groups where the binary operation is not commutative. It's always associative, but in some groups it may not be commutative. So we make this definition, and it's a remark rather, but it's more of a definition than a remark. A group in which the binary operation is commutative is called an abelian group. So whenever you hear the expression abelian group, that means that the binary operation is commutative. Now, without any further ado, we will do a bunch of examples, I promise. Our first example. This boldface Z represents the set of integers, and the set of integers under the binary operation of addition is a group. Let's convince ourselves of this. And let's see. Is the set of integers closed under addition? Yes. So to every ordered pair of integers, the operation of addition assigns another integer. The binary operation is associative. As a matter of fact, addition of associative, yeah, that's right. Addition of real numbers in general is associative. So x1 plus x2 plus x3 equals x1 plus x2 plus x3 for all x1, x2, x3 in Z. And in fact, this holds not just for integers, but for all real numbers. Let's see, what else do we have? An identity, okay. What is the identity element in the set of integers? What do you add to any other integer to get that integer? 0? And now, can we back that up? Yeah. Let's see. 0 plus x equals x. X plus 0 equals x for all integers x. So we have an identity. And let's see, every number has to have an inverse. Every integer has to have an inverse. So under the binary operation of addition, what is the inverse of an integer x? It's the number negative x, or the integer negative x. X plus negative x equals the identity. And negative x plus x equals the identity. So every integer x has an inverse. Addition of integers is commutative, and that follows from the fact that the integers are a subset of the real numbers, and the real numbers in general are commutative under addition. So since this operation is commutative, the integers form an abelian group under addition. Another example. The set of positive rational numbers under the operation of multiplication. If we take two rational numbers and multiply them together, do we always get a rational number? Specifically, if we take two positive rational numbers and multiply them together, do we always get a positive rational number? And the fact of the matter is we do. Remember what a rational number is. It's a number that can be written as the quotient of two integers, the denominator, of course, being non-zero. So pick any two positive rational numbers. Then there exist integers mn, rs, and let's see. Since we're talking positive rational numbers, we can assume that all of these guys are natural numbers, positive integers. Let P and Q be any positive rational numbers, period. Then there exist natural numbers, M, N, R, S, such that P is the quotient of two natural numbers and Q is the quotient of two natural numbers. Remember, if we multiply integers together, we get integers. And if we multiply natural numbers together, positive integers, we get natural number times natural number is a positive integer, natural number. So we note that the product of these two rational numbers is the quotient of integers, actually more specifically the quotient of positive integers, in other words, the quotient of natural numbers. So the numerator is a natural number, the denominator is a natural number, which means that the product is the quotient of two natural numbers. So it itself is a positive rational number. So the positive rational numbers are closed under multiplication. Let's see, is this associative? Yes, and we'll use the fact that the positive rational numbers are a subset of the real numbers, and multiplication of real numbers is associative. Multiplication of all real numbers is associative, so certainly multiplication of positive rational numbers is associative. What's the third thing that we have to have in order for this to be a group? Isn't it that we have to have an identity element? Do the positive rational numbers have an identity element? Is there some positive rational number that we can multiply any other rational number by and get that other rational number? What do you think? If you're thinking 1, you're right. 1 is a rational number. It's a positive rational number because we can write this as the quotient of 2 positive integers, 1 and 1. One is the identity not just for the rationals, but for the whole set of real numbers. 1 times anything is that anything. Anything times 1 is that anything. So 1 is the identity. What's the only thing that we need now? Every element has to have an inverse. Now to see this, let's note that since x is a positive rational number, there exist natural numbers m and n such that x equals m over n. M and n are positive integers. And we note that y equals n over m is also a positive rational. So what? Well, x times y, x is m over n, and y is n over m, which is 1, the identity, and y times x is equal n over m times m over n, which is also the identity. So every element has an inverse. All 4 group axioms are satisfied. So the set of positive rational numbers under the operation of multiplication is a group. All of the four group axioms are satisfied. And is there one more thing maybe that we can say about this group? What about commutativity? This is an abelian group. And we can just use the fact that multiplication of real numbers in general is commutative. And since the positive rational numbers are also real numbers, the multiplication of positive rational numbers is commutative. So the positive rational numbers under multiplication form a group, and in fact form an abelian group. This is a similar example. Again, we're going to take the rational numbers positive and negative without the element 0. So all of the rational numbers except for 0. And we claim that this is a group. And the first thing that we have to do is establish that multiplication of non-zero rational numbers is closed. So we take any two non-zero rational numbers. By the way, this represents the entire set of rational numbers with the element 0 removed. And to show that the set of non-zero rational numbers is closed under multiplication, we take two non-zero rational numbers, p and q, and we say that there have to be non-zero integers, m, n, r, s, such that p equals m over n, q equals r over s. And the product of the rational numbers p and q is m over n, r over s, which is integer m times integer r over integer n over integer s. And both of these are non-zero. Non-zero integer times non-zero integer is non-zero integer. Non-zero integer times non-zero integer is non-zero integer. So p times q is non-zero integer divided by non-zero integer. It's a non-zero rational number. So the operation of multiplication is closed. Now let's see, what do we have to have next? Multiplication is associative. And there's an O in here somewhere, I think. There we go. And here we're just going to use the fact that the multiplication of all real numbers is associative. And so that applies to subsets of the real numbers as well. Third thing, we have to have an identity. And the number 1 is going to be the identity again. 1 is in this set. It's a non-zero rational number. And 1 is the identity. One times anything is that anything. Anything times 1 is that 1. So this is the identity. And finally, for each non-zero rational number x, there exists a non-zero rational number y. Such that xy equals the identity 1. And what is y going to equal? The rational number 1 over x. Now, the only thing I didn't show was why this thing is a rational number. But if x is a rational number, a non-zero rational number, then we have non-zero integers non-zero integers m and n. So that's the integers minus the element 0. Such that x equals m over n, quotient of 2 non-zero integers. But that implies that 1 over x is 1 over m over n, which equals n over m. Quotient of 2 non-zero integers and so it's a non-zero rational number. So the set of rational numbers minus the element 0 under multiplication is a group. And in fact, there's one more thing we can add to this. We can also say it's abelian, because the multiplication of rational numbers, in fact, the multiplication of all real numbers, is commutative. So this is not just a group, it's an abelian group. Now let's look at something that fails to be a group and talk about why it fails to be a group. Okay, here's an example of something that's not a group, which means that at least one of the group axioms doesn't hold. But which one is it? Do you have an idea? Let's go down the list. First one is multiplication closed on the integers. I think it is. Integer times integer is integer, so that's not it. What about associativity? The integers are a subset of the real numbers. And multiplication of real numbers is associative. So associativity is not the problem. Is there an identity element? One, which is an integer, is the multiplicative identity. 1 times z equals z, and z times 1 equals z for all integers z. We're running out of properties to test here. We have an identity, we have associativity, the operation is closed. Does every element have an inverse? Let's see. Maybe the negative numbers are the problem. Let's see. Oh, wow. Most of the negative numbers are a problem. Most of the positive numbers are a problem. An element has an inverse if we can multiply that element by some other element in the set and get the identity 1. You know what? It looks like the only two integers that have an inverse are 1 and negative 1. One is its own inverse. 1 times 1 equals 1, the identity. And negative 1 is its own inverse. Negative 1 times negative 1 equals 1, which is the identity. And that's where it stops. No other integer has a multiplicative inverse. Check it out. 0 certainly doesn't. Zero has no inverse. What are we going to multiply 0 by to get 1, the identity? 0 times anything is 0, so there's nothing we can multiply 0 by to get the identity 1. But 0's not alone. 3 has no inverse in the integers. Is there an integer that we can multiply 3 by to get 1? The identity? No. The only candidate for an inverse for 3 is 1/3. And 3 times 1/3 does equal the identity 1. So what's the problem? 1/3 is not an integer. This set doesn't contain an inverse for 1/3. This set doesn't contain an inverse for 1/2. This set doesn't contain an inverse for 3. It doesn't contain an inverse for 2. It doesn't contain an inverse for 5. It doesn't contain an inverse for -4. It doesn't contain an inverse for any integer other than 1 and -1. Okay, so that's the problem. And I guess we can sort of give a very insightful general answer. No elements of the integers other than plus or minus 1 have a multiplicative inverse that's also an integer. So that's why the integers under multiplication fail to be a group. Wonder if I can come up with another example of something that fails to be a group. Okay, here's an example of something else that's not a group. The set of even integers under multiplication. Let's see what happens here. Are the set of even numbers closed under multiplication? Yes, but remember, even times even equals even. So the product of two even numbers is an even number. Our binary operation is closed on the set of even numbers. Is it associative? Yes. E is a subset of the real numbers, and multiplication of real numbers is associative. Since multiplication of real numbers is associative, the multiplication of subsets of the real numbers is also associative. Okay. Well, what about the identity? Oh, wow. the identity should be 1. One is the multiplicative identity. But 1 isn't an element of this group or this set. So here's a problem. No identity. And is that the only thing that prevents the even numbers under multiplication from being a group? Well, let's just go to the fourth property, the inverses, and just see if every even number has an inverse that's also an even number. And again, we're acknowledging that 1 is the identity, and it's not even an even number. So 1 is the identity, but it's not an even number. And here we find out that for every even number, there's no other even number that is its inverse. For example, 2 is an even number. What do we multiply 2 by to get the identity? 1/2? But that's not an even number. The inverse of 2, which is an even number, is 1/2, but 1/2 is not in this set. So in the set of even numbers, the element 2 doesn't have a multiplicative inverse. And we can make that same observation about any other even number. 0 is an even number. There's nothing that we can multiply 0 by to get the identity 1. And 10's an even number, but there's no even number that we can multiply 10 by to get the identity 1. So here's another example of a set in a binary operation that fails to be a group. Now let's make some observations about the identity and the inverses in a group. We're going to end this lecture with 2 classic theorems about groups. And we want to pay attention to the proofs because these are important proofs to know how to do. Both of these theorems have proofs which are what we call uniqueness proofs. And usually, I won't say 100 times out of 100, but I will say 99 times out of 100. Whenever we try to show that something is unique, we use the strategy that we're about to employ in proving these 2 theorems. So uniqueness proofs are things that we're going to have to learn how to do if we're going to stay in math. And they all use the same trick. We're going to use the same trick in this theorem that we use in the next theorem. So that's why we want to pay attention to these proofs and learn how to use the trick that we employ in these proofs so that that trick and that mindset becomes part of our own mathematical repertoire. Okay, here we go. We can do this proof by contradiction, but we don't have to. The proof is pretty much the same regardless of whether we do it by contradiction or not. And since we don't have to do it by contradiction, we won't. And if I've been saying the word inverse, I apologize. I should be saying identity. We're going to show that the identity of the group is unique, and we're going to use a proof that doesn't rely on contradiction to show that the identity is unique. Suppose that E1 and E2 are both identities in the group G. Now notice that I didn't say that E1 and E2 were distinct. We're allowing for the possibility that they are distinct, but by not saying that they have to be distinct, we're also allowing for the possibility that they're one and the same. If we do the proof by contradiction, we're going to insist that they be distinct, and that's going to give us our contradiction. But if we don't do the proof by contradiction, and we do it the way that we're about to do this without using contradiction, we won't make any claims or stipulations as far as whether E1 and E2 have to be distinct or not. We didn't say that E1 and E2 were distinct. We didn't say that they weren't. But we just said, suppose that they are both identities in the group G. So maybe E1 and E2 are distinct, maybe they're not. It doesn't matter for the proof that we're about to do. We're just using the definition of identity here. If E1 is an identity, then E1 star any element is that element. And any element star E1 is that element. That's by the definition of identity. And we're going to make the same statement about E2, since E sub 2 is an identity by hypothesis. So we've made similar statements about E1 and E2 using the definition of identity. And essentially what this proof amounts to is we'll assume that both E1 and E2 are the identity and let them compete with one another. And it will turn out that they have to be equal. And that's typically what we do in a uniqueness proof. We'll assume that there are two of whatever it is that we're trying to show are unique. Let them compete with each other, and in the end it will turn out that they have to be equal, showing that there can't be more than one of them. Okay. So let me think about how I want to write this now. Let's see, I haven't got it written that way. Let me write it this way. Okay. And what did we use to justify this? E1 is our x here. X times E2 is equal to x because E2 is an identity. Okay. Now let's do the same thing all over again. Oops, 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 oops. Here we're going to use the fact that E1 is an identity. And really, let's see, what property up here did we use? Specifically that. Here, E2 is our x. E1 star x equals x. So E1 star E2 equals E2. Yes. E1 star x equals x for all elements x and g, and that includes the element E2. So E1 star E2 equals E2. And up here, we use this property, x star E2 equals x for all elements x and g, and that includes the element E1. So for x equal E1, we have E1 star E2 equals E1. Oh, but now we combine these. Yeah, E1 star E2, it's equal to E1. E1 star E2, it's also equal to E2. So E1 equals E2. So we assumed that there were two identities, E1 and E2. And that assumption led us to the fact that they had to be one and the same. So if there are two identities in a group, it turns out they're not distinct identities, they're one and the same. They are unique. Oh yes, and I forgot to put the little square down here that shows that the proof is complete. But that's the proof, and that's essentially how we do a uniqueness proof in math. If we're trying to show something's unique, we assume that there are two of them, and then we show that those two have to be one and the same. That's the strategy. Here we're about to do another classic proof involving uniqueness. Given the group G star, the inverse of X is unique for every element X in G. So take any element X in the group G. It has an inverse. It has to, in order for the group to be a group. But it's going to be the case that the inverse of X for any element in the group is unique. And we use the same trick we just used in the previous theorem. We suppose that X has two inverses. And we'll call them Y and Z. That we're saying that Y is an inverse of X, and we're saying that Z is an inverse of X. But we're not necessarily saying that they're distinct. We're not saying they're not distinct. We're just saying, suppose Y is an inverse of X and Z is an inverse of X. Maybe they're the same, maybe they're not. We're not saying. Now, since Y is an inverse, X star Y has to equal the identity, and Y star X has to equal the identity. And the reason is because Y is an inverse of X. And we're using the definition of inverse. Now, we're also going to say this. We're going to make a similar statement about Z. X star Z is the identity, and Z star X is the identity. Because Z is an inverse of X. And we'll let Y and Z compete with each other for the title of inverse of X. So let's see what happens. Y is equal to Y star E, because E is the identity. Nothing earth-shattering there. But let's see, X star Z is equal to E, right? So this is E. E, the identity, is equal to x star z. So that's where this comes from. And now, look what I do. How was I able to go from here to here? What allowed me to go from here to here? I used the fact that the binary operation is associative, didn't I? Okay. So we can do that by associativity. But let's see, what do we know about y star x? Y star x is also equal to the identity. And we find that out right up here. Y star x is the identity. So this is E star z, and that's just z. Well, look where we started in this equation, and look where we ended up. Our two inverses turn out to be one and the same. So the inverse of x is unique. We assumed that there were two. We assumed there were two inverses, y and z, and it turned out that they had to be one and the same. So they are definitely unique. These are standard proofs in algebra, and they carry over to other areas of mathematics also. Now, are they easy proofs? You know, it looks like they're easy here. But if we try to do these without looking at the video or without looking at our notes, we might actually get stuck, because even though they look pretty simple, they're not. So these are proofs that we should master. And if we try to do these and we get stuck, it's not cheating to look at the video or peek at our notes and see where it is that we're getting stuck. We may have to do these proofs a number of times before we really master the thought process completely. But if we're going to stay in math permanently, this is a proof, or these two proofs are proofs that we should master. We're going to apply them again and again. Uniqueness is a big thing in mathematics. There are going to be times when we have to prove that something's unique. And the strategy is almost always the same as it was here. So these proofs are worth learning. Even if we have to do them several times to learn the thought process and peek in the notes or peek at the video as we go. There's nothing wrong with that. I've probably said this to you before, and I'll say it again. Isaac Newton, he invented calculus. He was genuinely the Albert Einstein of his century. He made enormous contributions to math and science, and yet he's quoted as having said this: "If I have seen farther than others, it's because I stood on the shoulders of giants." And by saying that, he was acknowledging that he was able to do what he did because of using the accumulated wisdom of all of those who came before him in building on what they had learned and accomplished. He had taken their knowledge and assimilated it and made it his, and then he built on it. And that's what we do in math. We take the accumulated knowledge of all those that have come before us, make it our own, we assimilate it, and make their mindset our mindset, and then we build on that. So there's nothing wrong with working through things a number of times to learn something by repetition until finally we go, oh, I got it. I don't need the notes for this anymore. Uh, I know what it is I've been missing. I can do this without the notes. We chuck the notes, we start fresh, and we do it from start to finish. Yep, I can do it. I knew I could do it because now I can see from start to finish how it works. I get the big picture. There's nothing wrong with doing some things by repetition a few times and peeking at the notes to see where it is we're getting derailed. What we're doing is we're making the wisdom of other people our wisdom and the thinking of other people our thinking. And when we do that, we're standing on the shoulders of these giants, just like Einstein stood on the shoulders of giants in his century. So these are proofs worth mastering. And they're not as simple as they seem. They seem very simple, but when we try to write them out, we may get stuck. We may get stuck. So let's work through these a few times. These are proofs that we should know how to do because we'll be called on to do these over and over again in mathematics. Class dismissed.